Great. Good morning, good afternoon, good evening, wherever you are in the world. Welcome everyone back. This is our third season of the Future of Urban AI. This is a collaboration between Urban AI based in Paris and Cornell Tech in New York City. We're really excited to bring another 8 webinars every week at the same time, today through November 13th. This year's theme is looking at the shift from generative AI to adaptive cities. So trying to understand how some of the new technologies that have grabbed headlines over the last year are going to be put to work um, uh, for urban climate action, particularly to boost adaptation and resilience. So here's the schedule. This is available in Eventbrite. We'll also share it again at the end of this session. One key difference from last year is that we are keeping a firm schedule. We're going to be every Wednesday at the same time for all 8 sessions. Last year we had some shifts, but those will be on schedule this year. So without further ado, I'm going to turn the table over to Saining Z. He's an assistant professor of computer science at NYU Current, and we're going to be learning about what happens when you unleash AI agents in virtual worlds. I've seen this presentation before. It's really exciting, and I hope you all enjoy it. So Saining, over to you.
All right, yeah. Thanks, Anthony. Welcome everyone. It's really exciting for me to be here. And my name is Saining Xie, and I'm assistant professor at NYU, Department of Computer Science. So our research group really focuses on artificial intelligence and computer vision. And today I'm going to be talking about one of our recent work that I think has really strong connections to urban tech and urban AI. And I'm looking forward to taking this opportunity to discuss it with you all. So this is in collaboration with several other researchers at NYU and also like Hong Kong University. So I do have like a little kind of a demo video like I wanted to show before we delve into this work. But unfortunately, I think the audio doesn't work, so you probably can't hear the sound, but it's just like music. And if you're interested, I highly recommend like just to go into our website, search the keyword, and then you'll find this video on YouTube. But I'm gonna play this anyways. All right, I'm gonna stop here. I hope this will give you just like quick overview. Again, like I think without music, it's less fun. But let's just like delve into the technical details of this work. Um, so this is the V-IRL or VIRL, like our new AI agent environment. But the first thing I wanted to talk about is, why we want to do this. And from kind of an AI researcher, especially, kind of researcher's point of view, like why grounding virtual intelligence in real life is such an important research problem. So for many of you, if you're coming from very different background, I just want to tell you a few things about like AI agents. So it has been kind of like a buzzword recently, but the standard framing of an agent in AI or traditional AI and reinforcement learning is the following, right? So you'll have an agent and it will take an action in an environment, which will be interpreted into a reward and also representation of a state. And then like this reward and the state will be fed back into the agent. So you have this closed loop of an agent and also environment, and they interact with each other. And recently, I think this large language model based agent has been extremely popular, right? It really is about like, how we can actually transition LLM from just a standalone chatbot to this nearly autonomous agents capable of, I guess, outsourcing tasks and adjusting their behavior in response to inputs from their environment or themselves. Okay, so this new kind of agents can now run applications to, I guess, search the web, or kind of solve math problems, do coding using different tools, and even act, on user prompts to check and crack their work, right? So it's kind of like a very complex pipeline, but the large language model is definitely the brain of this, large pipeline. And the whole system really operates by receiving and outputting kind of language prompts. And as you can see from this figure, I guess, which is already quite outdated from last year, there's been a monumental explosion in this space of AI agents or large language model-based AI agents. So this rapid growth really, I guess, showcases an increasing capabilities of AI across very different applications. And Stanford's generate agent paper, I guess, is one of our main motivations. So in their work, they actually deployed AI characters that live in this virtual sandbox game world, right? They act and make decisions like real people, and they can remember past events, and they can also interact with other agents and plan their actions. I think one of a cool example they said in the paper is, like after a few rounds of interactions between different agents, they actually throw a birthday party or something without any kind of a real human intervention. But one of the problem is all these actions all happen in this textual space. And this game animation you see here is basically just rendered from the text. So for the large language models to do the planning and reasoning to create these agents, none of this kind of real content have been used. Another very related area is the so-called embodied AI. So embodied AI really focuses on the interaction with the real world and also the real physical world. So people study this problem embodied AI, I guess, mainly from two directions. One is like really building the simulated environments for example, on the left side, or study, robotics, right, with real robots as a hardware. But they all have their own kind of problems and limitations. For examples, in simulation, just because we won't have, the best kind of a game engine to do this. So usually you'll see kind of Unreal visuals. Maybe I have video here showing. Yeah, like usually this will be kind of simplistic indoor environments. And you can see even if like this agents can perform some actions, it's like not very real. It's like a game maybe from 90s. And I think in robotics, there are also like problems. For example, due to the hardware constraints, the task definitions usually will be very narrow, and the data collection is very challenging. And also, it's also kind of constrained to this simplistic lab environment, but not real world. Okay. And another motivation is the development of open world computer vision systems, which means like we really want to move away from a fixed set of, classes for image classification and all these kind of predefined tasks, like object detection, and we want to make computer vision systems generalizable to really diverse and real world problems. And people have been studying this, I guess, like for a while now. And the common way to is really to expand the data set size for training such computer vision systems. But the problem is, despite having larger and larger data sets, I guess like the geographic coverage is still quite kind of biased and limited. And we really don't have an open world system right now, but rather we have kind of like moving towards a more like an open internet system, just because all these data sources are still from the internet, right? Like the images, the photos people uploaded to, Flickr, all those kind of sites. But they are kind of a snapshot of the real world, but there's still like a domain gap. Okay. So to summarize, I think this is kind of like a simple problem statement. The V-IRL, like our platform and our agent, is closely related to AI agents, embodied AI, and open world computer vision. But we want something extra, right? So we want to have maybe a heavier usage of real information. We want it to be perception centric rather than like large language model only. And this will be really helpful in terms of like interacting with the real world content, just because, like when we're in the real world, a lot of times we're not just like looking at text, right? Or like we're not just like facing a chatbot, we're looking at a lot of visual signals. And also like in terms of like embodied AI, we want our tasks to be more realistic. It needs to be richer and to be, kind of like more diverse. In terms of like computer vision system design, right? We want to kind of redefine the concept of open worldness. And we want kind of real thing captured in real life. We want it to be, again, very diverse. And it can be just noisy, but it has to be kind of corresponding to what we can observe in real life. And then like hopefully the real information can be multi-source and can be kind of live, right? Can be up to date rather than just taking the static data sets from the internet. So I think the TLDR for our platform, so V-IRL or V-IRL is an open source platform building and testing agents in a real world setting that really makes the rich sensory grounding necessary. And we also want to develop a diverse kind of exemplar agents that I'm gonna show you in a few slides to showcase the platform's use cases. And also, like I think once we have this environment and this agents, it also becomes a very good large-scale benchmarks to measure the performance of the foundational language and vision models. So this is our paper. So the first thing I want to show you is some of the kind of exemplar agents. You can think this as just like individual demos. But they all kind of like are connected with each other and they're all supported by our platform and the environment. So like basically we have this kind of 8 agents, and basically we give these agents some character persona that includes some kind of meta information about the specific agent, including like a name, a short kind of bio, and also like very important, an intention they are trying to accomplish, and also like a fun kind of a avatar for them. So let's study them one by one. Okay, so the first thing is, like one characteristic about our work is our agent are Earthbound, which means like, with this geographic coordinates as link between the digital media and the real world, our agents can ground themselves in the world using basically the APIs for maps, and also like the real street view imagery from Google Maps. And also like because they are earthbound, they know the information about the nearby destinations and so much more, right? So all this information are the real content from our real world. So here's a kind of quick, very kind of naive example. Like this is an agent or a character. His name is Peng. He's like a student, I guess like visiting NYU. He needs to visit several locations throughout the city to get documents signed for registration, blah blah blah. Right. So this is basically like our input to the large language model. And then the task is given a starting address and list of waypoints. Plan the shortest route to all waypoints and follow it on the straight wheel. So essentially, because our large language model system, our agent system can really call the APIs and really kind of interact with Google Maps. So we can really try to accomplish such tasks where given kind of like a few kind of waypoints, we can actually find the shortest path to travel. That kind of saves a lot of time for Peng. But this is just like the simplest example that shows like our large language model agents can be connected to this API function calls of Google Map. And we can also tackle more complex tasks. So now we can actually design a proper kind of language-driven agents. And now you have like large language model involved. This can really enable agents to reason, to plan, and use external tools and APIs. So we have like two examples. Yeah, I'm just gonna skip this maybe. Yeah, it's too slow. But essentially, these two agents, one is like really good at place recommendation. So again, based on like some really initial intention, let's see, oh, like Peng is a student visiting from China, and he's like new to New York City. He would just say something, about like the food type of food they like, and this agent area will do some place recommendation, right? And purely based on the language input. So of course you might ask like, oh, okay, and this information is probably already there. Like, when we are trying to find a good restaurant, and maybe we'll just go to the Google Maps, search for nearby restaurants, and maybe take a look at the user rating and also like user reviews, and then that help us to do the decision making, right? So essentially, this large language model can do the same, and then like they can really aggregate all this information, considering the location, considering the type of food you like, and considering all this kind of user reviews to give you kind of like recommendation. And similarly, we can really create this kind of real estate agent as well, and for like recommendations about like apartment renting, right? So in this case, it's really interesting just because Google Maps doesn't really offer this information immediately, right? But our large language model driven agents can actually call an external API, which we used in Zillow API, offered from a completely different website. And then now we can actually grab this information from outside, merge it with our kind of intention and the user kind of meta information, and also like this kind of geographic information from Google Maps, and then provide a kind of consolidated recommendation for the user. Okay. And then this is still like, just the purely language-driven agents, right? You just like parse the information from the internet, calling different kind of APIs to get this information to perform some form of kind of decision making. But what's really, really interesting is this virally grounded agents that we tried. So that means like the agents not only can just read text, but it can also perceive the real world like humans. So this is one example. We have this one agent called Urban Assistance Robot. And the goal here is to just like, cleaning the streets, right? So I'm just gonna show this like little video here. So essentially, this is kind of like in New York City, our agent is basically kind of like, traversing each of the streets. And then, this is kind of using computer vision, right, systems like segmentation and object detection. They can find all these trash things, and then we rely on some again like some other computer vision tools to make sure like we don't double count things and so on. But then like now imagine like this robot can just like, roam on the streets and find all these trash cans. And this is really open world because, like we really not teach or train the computer vision system with the specific data set distribution, right? This is completely, generalized from an existing computer vision system that was pre-trained on other data sets. And there are like interesting examples where, you can also localize and identify some downstairs. Okay. And this is my favorite example. So we have like this agent called Imani, and she's about is like she is a sustainable urban development graduate, and she's trying to, analyze distribution of, a few things like this public facilities like trash bins, fire hydrants, and public can park benches in Central Park. So what we did is like we actually create this agent and we deploy this in Central Park in New York City. And we run this program for about like 5 hours, right? So what you can see here is actually a heat map of all the detected trash cans and fire hydrants and benches. Um, so I'm not sure if this is kind of an easy task to do because one of the problem is you cannot get this information purely from a satellite imagery, right? Because a lot of times these trash cans, they are just like, kind of like blocked by the tree or hiding behind the building. It's really hard to get this information from a top-down satellite imagery. But like we can, by having this agent, just like the previous example, by having this agents kind of roaming all the streets, like, in Central Park, we can gather all this information. And you can find something kind of interesting. Like after we have this heat map, we try to, manually examine what actually those agents discover. Is it accurate? Is it really kind of like a trash can? Let's see. And it turns out the accuracy is very, very good. So like the agent can always find this kind of tiny trash cans in different locations. And we find something interesting, right? Like I'm gonna skip some of these examples, but like from the heat map, we see I think it's probably somewhere here. Yeah, we see like there's a location here. You can see like maybe like little red in the region here. It means like there are like so many trash cans in this kind of one street. So we just like say, oh, what's going on? Is there a bug in our code or something? And then like if we just like zoom in and go to this location, you can see, yeah, there are definitely multiple trash cans, like 4 trash cans in this kind of like very close by locations. So that's kind of like a very interesting thing. And I think it can be very insightful in terms of like, planning and designing the public facilities. And also like this can facilitate other applications. For example, in this case, Hero is another kind of like tourist or student and exploring, he's just like doing kind of some random walk in the city, right? And he wants to find a good lunch spot with food that's not too spicy. So again, like we can see in this example, like this agent is just like, given a starting location in this Google Street View, right? And then like he'll just randomly explore. But the really interesting thing is like sometimes you need to make a decision, like in this case, right? About like whether I should turn left or turn right, or I should just like keep going forward. But because we have like AI powered and large language model and kind of like a multi-model powered AI agent, so like the agent can really decide on their own and saying like the left row has more kind of residential feel to it, which usually means like cozy family-run spots serving up the kind of real deal local food. But anyways, so I think this makes sense because again, remember the agent intention is to find a good lunch spot, right? So it makes sense to go to like maybe a residential area rather than going to the main road. And then like you can continue and the good things like this AI agent can also recognize, different storefront. Like for example, in this case, agent recognize, oh, there's a restaurant like might be good for lunch, but based on like the OCR and text rating of this storefront, even if it's in kind of a Chinese, it says still understands like this is actually offers spicy food. But then like because the user intention or bio tells us like Hero doesn't really like spicy food, so he chose to skip this location, right? To skip this restaurant. And then until he identified another place, I think uh, here, right? And then like, it says, oh, this place seems like, it serves diverse and local cuisine. And by the way, this information is again by, spotting the text on the storefront first. And then because our agent Earthbound, so you also know the GPS coordinate of this location. So they can then go back to the Google map and then check the user ratings and basically like descriptions of this restaurant. And then this will be used for this kind of decision-making process. Okay, so finally, we have some even cooler agents that's kind of collaborative. In this example, I'll just show you the video. Like Ling is tourist, and unfortunately, her iPhone screen just cracked. So she really wants to find the kind of like closest, Apple store to fix her phone. And then like she's trying to but she's like new to the city, so she doesn't really know where to go, and also like her phone was broken, right? So she asked like a local kind of a resident, and the local tells her like you should turn around and head west, and when you see a Starbucks sign you turn left, blah blah blah, right? This is called like visual language navigation task. So basically, like, one agent is providing kind of verbal or language-based instructions in terms of like navigation, and your agent need to kind of like be able to observe the real environment to find this kind of like locations or this intermediate kind of queues like Starbucks to be able to know where to go. So this is kind of a very interesting example because Ling actually failed for the first time. She was not able to locate this Apple store. I'll tell you why. Um, yeah, but then like what Ling does is like she can actually ask for another local, and this new agent says, "Oh, you already kind of passed this location. You should just turn around. You will see it on your left." So actually, at the end, I think Ling finally found this kind of Apple Store here. But what's really going on is here, actually, Ling actually passed through this Apple Store on the right side, just because the fancy design of the Apple Store in San Francisco, the wall is pure steel, there's no logo. And actually, Ling doesn't, like she just doesn't know, right? So she get passed to it. And only until she kind of turned around and see this Apple Store again, so she can recognize this is actually, the destination she want to go. And finally, I guess like this is also like one final kind of agent that we want to show. Basically, this is also kind of real use case. So I wonder if you have done this before, right? Like basically, maybe you are going to a new city and then you want to ask ChatGPT and say, oh, like I have this, one day, free time. I want to just like tour the city. Can you give me a kind of personalized plan? I want to explore some, like less popular places. If you don't do anything, the ungrounded large language model will definitely give you a plan, right? But the problem is like this plan might not be very good. So like in this case, if we do this for ChatGPT, they'll say, oh, we go to Chelsea first and we travel to like Brooklyn, and then we'll go to Bronx, right? It doesn't really care about the commute time, right? If the time takes like maybe 1 hour, it doesn't make sense to really have this consecutive actions. And also, it doesn't really care about your kind of like mental and physical state. So, so it doesn't really care if you will be tired or not. It just like give you this plan. But because we have our kind of Earthbound agent and we have like this real information, we can really have a much better plan considering the commute time and also considering your mental and physical states, right? Like maybe, through the planning, like the agent actually will refine their own plan considering like, how hungry you are. Like maybe if you're hungry, you should go to a restaurant for lunch. And if you are like, like if there's too much stress, like maybe you need to go to some more relaxing places. It also considers the budget as well. So the cool thing is like now the agent can actually interact with you, right? You means like real humans. So you can actually do some human intervention here, but adjusting your physical and the mental states. And then like the AI agents can adjust their plan accordingly. And again, like this is a multi-model system. So our agent can also be deployed to, kind of help you to tour this place in your plan first, right? Like maybe there's a park and Diago actually, this agent can actually traverse these regions of interest and find, scenery kind of spot to add this to your itinerary. So I think this is kind of very cool. It's like really personalized and it's really, down to the earth. So we don't have much time. I just want to quickly go over some of the system fundamentals. Um, and like this is powered by a few things, powered by Google Maps, powered by large language models, and powered by a multi-model system. I'll skip the detail, but basically we have this kind of hierarchical pipeline where we have environment and the algorithm, the foundation models with computer vision and language model can really kind of like interact with the environment, and then that makes the agent have this perception, reasoning, action, and collaboration capabilities that can fulfill the agent intentions at the top of this figure. So again, like this is a good benchmark as well. Like we can do place localization using this environment to benchmark the performance of this open world computer vision systems, because this is kind of like key, requirement for making, decisions, right? Just like what we have seen in this example, finding a launch spot. We can do VQA tasks as well, question answering tasks. And in this example, like our question will be which human intentions can be accomplished here, right? Like you can see something here, and like we have multiple choices for the AI agent, like AI model to answer. And there's only one, real question. And we know this question because we have this information. And this information is real information that we can fetch from the Google Maps. And we can perform the vision language navigation as also like a quantitative kind of like evaluation task for AI models. And finally, I want to say one thing. So this is really not just like one city, just because Google Maps support like, multiple cities across the globe. So we can really study the capabilities and limitations of AI models across like very, diverse kind of geographic diversity. And some of this kind of key insights that we discovered, like maybe this will be really related to the AI application in urban technology as well. So vision models really struggle on cities like Tokyo and Hong Kong and Buenos Aires. And in triggering observations, like their primary use of non-English language in street views might be a problem here, because all these foundation models are trained with, English-centric data sets. So, it's perfectly fine for developed countries, Western countries, like especially in New York, in London, the performance is pretty good. But if you talk about like, countries and cities in Asia, the performance degradation is pretty significant. And another thing is like vision models might also struggle in, like non-developed regions, like such as Lagos, where we tested. So I think it's just because the non-traditional street views relative to the more developed cities. So a few like maybe comments here, like why generative AI is important for urban technology. I think we are really having this kind of transition from a piecemeal approach to more of an end-to-end autonomous agents. That means like before, like for kind of urban planner, like they might already use some of the AI tools, such as like maybe classification models, like detection models. But right now, we can really have a much more intelligent information aggregation and analysis kind of pipeline powered by kind of a more holistic AI approach. And also like the current interface is purely through natural language. So this really provides a new and also like more accessible user interface for urban designers. And I think this will be also very helpful to just like make it bigger than just like one city effort, right? This can be really done at a global scale, and we can talk about like multi-city collaboration and so on. And finally, I think what I wanted to say is like urban is also very important for generative AI, like for us as an AI researcher, because one, like large language model is not enough, right? We're in this living in this real world. And actually, the urban setting, this urban environments, the cities that we live in is a perfect scenario for this thing called like visual spatial intelligence. We need to make decisions based on what we see, and we need to be able to act, right? So I think this really represents a very important transition from the digital world to the real world. It has implications in how we can benchmark AI models. It has implications like on where can we actually find new data source, right? And also like, we can actually create this kind of like closed loop of perception, reasoning, and action in this urban environment. And also, like, I think it's really kind of critical for us to discuss like AI safety, fairness, and ethics. I think like there's no better kind of environment or kind of setup than urban design, urban planning for such kind of important issues. So that's the end of my talk, and you can find all the code if you want to play with our demos, if you want to check out like our videos and blog posts. It's all there online, and we're actually going to present this at the ECCV conference next week.
Great.
Okay, yeah, thank you, everyone. Happy to discuss more.
Thank you so much, Saining, for this is a fascinating presentation. Yeah, I've been thinking about this since the first time I saw you share this about 6 months ago. And hearing it again today, I mean, there's so many fascinating directions to take the conversation, but one thing that strikes me is, there's this movement towards building digital twins of cities that is very much a sort of formal, like kind of data curation process that involves like formal schemas and kind of like very structured connections between different data sets and then building very elaborate interfaces on top of it. And I think what you've shown is that agents can really assemble digital twins on the fly, right? We can kind of unleash them with very focused tasks, and then they can go and find the information that's relevant. And then that can scale up. That's the really fascinating part of it. It's not just about personal assistance. It's about really swarms of agents kind of assembling these virtual cities. And I think that's a way of approaching that challenge that is really flexible, and I think will really have some impacts on how that moves forward. I'm curious though, just in terms of like the computational cost of doing this, like what's involved in running one of these agent simulations? Like, is it something that we could imagine running on a phone, or is it phone plus cloud, or is it a giant server farm dedicated to just doing this?
Yeah, so I think it's not that hard actually, just because a lot of this are through kind of like API calls. So we use like ChatGPT API a lot. And also like in terms of like the interaction with Google Maps, Google actually provided really kind of comprehensive documentation about like how we can actually use these APIs and so on. It's not free service, right? So like Google requires kind of like money. Um, like for using the APIs, and also like ChatGPT APIs also like has a cost. But like for example, in the setting where we tried this kind of like deploying AI agent in Central Park and run it for 5 hours, right? This I think the overall cost is like maybe I don't know $20 or something. But you can imagine if going forward, if this is really something that can be more useful, then we can talk about like collaborations with the companies. And I think let's see if Google wants to do this, I think they can actually build a pretty capable kind of like mobile app like everyone can use. And the real kind of cost for this, I think, should be very low because, again, you don't need to train such systems. You just need to do inference job on this large models. Yes.
Thanks. Other questions from the audience? Kuvera, I think you had a question. You want to come forward and share it?
Yeah, thanks a lot, Saining, for really the fascinating presentation. I was just wondering, maybe in a kind of practical perspective, when do you believe such technologies can be integrated into kind of real-time applications? And what obstacles do you see to such integration? Maybe hallucinations or others you mentioned? Yeah.
Yeah, exactly. I think we're already getting there. But like, one thing is like this research is not kind of like a standalone thing, like people kind of study this in parallel. This is basically what we want to achieve with kind of generative AI in large language models. So once we have like more capable, let's say, base model, once we have more capable kind of reasoning capabilities, right? Like for example, the recent launches like O1, like for example, like it really helps with this kind of reasoning capability for large language models because you can do the chain of thought. This has like direct kind of like implication for tasks like this, like V-IRL, right? So I would say like, we are getting there and the obstacles, just like what you mentioned, I think it will be how reliable this is, right? We showcases some of this kind of like example agents, but I would say like, we do encounter a lot of kind of failure cases, right? And largest problem is definitely due to hallucination, right? Sometimes these agents can just like, hallucinate and they can make wrong decisions. But if you say, oh, we want to deploy this for, urban planner or for just like, like everyone living in the city, right? Like I think we have to make sure the quality meets some of the requirement. And I think, but again, I think the nice thing is like we are like collectively, in AI, we're moving towards solving this problem. Thank you.
It looks like there's another question. Have you had any success in corroborating the trajectory made by each agent with traditional gravity models or something more macro like aggregated OD, I guess, origin destination data? So, sort of like established travel patterns from transportation surveys.
Yeah. So again, like I really don't understand the question, but this is a this is a good thing about it, right? Like I can see like maybe Zhishen, like
I think what he's asking is like, are you ground truthing
yes.
the plans or the predicted behavior based on like what we know about actual travel patterns in the real world? I think
Yeah,
that's
so we don't have any of this. So that's what I mean by I don't understand the question because I don't know what OD data is. But what I can say is like, because we are just working on like, a general platform. So all this data can be processed and can be integrated into this kind of AI agent decision-making process, right? So right now, I think we're only relying on, like those information that's offered by Google Maps, right? And Google Maps doesn't really have this kind of aggregated OD data. But because we know this is in a real location, so we can actually fetch this information from other sources, and we can get the gravity data or trajectories and so on. And then like, we can definitely integrate this together to have like more accurate predictions in planning. This is definitely possible. And this is why I also feel like fascinated about this type of research. It's just because it's so general. It's just like, kind of a layer that can connect multiple data sources. Yeah, that's my answer.
We have another question coming in that's basically asking like what are the implications of this work in light of Snap and Meta and others adding multimodal AI to their wearables? I think we saw the Meta Ray-Ban product out and building their own proprietary maps and services. And how would you see these agents working in those kinds of AR settings?
Yeah, it's a great question because I think this is my kind of dream. Because at the end of the day, we don't really want so many kind of virtual AI agents, right? Like what we want is like we can have kind of a really capable AI companion which may be kind of embedded in some of the variables, like Vision Pro or MetaQuest. And you can imagine like maybe you'll wear something and now you're exploring a new city, right? And then you will be like one of this agent, right? Like now you want to find a kind of good launch spot. And then like based on like whatever is captured through this kind of AR, VR devices, and then by consolidating information from the internet, the AI agent can really provide, individualized and personalized recommendations for you, right? So this is why, we also think like V-IRL can be just like a proxy to study this, because, I think there's still a long way for, AR wearable devices to become mature. Like everybody will wear this. I don't know how long it will take, like maybe a few years, maybe even longer. I don't know. But you can think about like this kind of Google Street Views. It's kind of like really coarse, noisy proxy towards this future, right? Like we can already study some of this AI in large language model based capabilities through this kind of platform. And then a lot of these kind of technologies, I believe, can be directly transferred to this kind of future scenarios.
Any other urgent questions? We're running a little over, so I think we'll say thank you. I just have a couple things to share before we go. So we have a couple new resources for the community that are being shared today. Can you guys see? Yeah, okay. As before, all the previous episodes from season 1 and season 2, the last 2 years of this series are available. We'll share this in the Slack channel and tinyurl.com/futureofurbanai. We also have a PDF report that's a wrap-up of last season, which is at this URL, and we will share that out as well. And then today we're also opening up a preview of a new horizon scan. This is a 10-year forecast looking at the future of urban AI with a focus on applications for climate adaptation. This isn't very much in kind of an alpha stage right now. It lives at futureofurbanai.org. So I would just encourage everyone to please go check it out, take a look at the content, explore this kind of graph of forecasts about the future, trends, signals of specific innovations. We're also going to be introducing some AI-powered tools that will allow you to generate your own customized insights off of this content. We're in the process of debugging that, rolling that out right now, so that should be available pretty soon. And then we also have a link to contribute new signals. So if there is something that you're seeing that you think is kind of a critical development shaping the future of urban AI, you can share that with us there, and we'll incorporate that into future revisions. And then just an invitation to everyone to put the series in your calendar. Join us next week. We're going to have a really interesting collection of researchers. Hubert will be the host for that session on October 2nd, looking broadly at some efforts that are addressing the applications of AI for sustainability in cities. So with that, just say thank you, everybody. Have a great day, and see you again soon.
Thank you. See you.
Thanks.
Thanks, Saining. Really fascinating stuff.